Yesterday, we participated in a lot of well-prepared talks about artificial intelligence, deep learning, data, and the problem with data we have to handle with. Today, we are going to combine all those things together to provide you a real case of study of our project. And I believe that we can do it in the best audience I can imagine. So I'm Marcin Stachowiak. I'm working as a senior software developer at Capgemini Poland.
And I'm Michal Dura, a senior big data engineer at Capgemini Poland.
So, ladies and gentlemen, good afternoon.
Okay, so the topic of our speech is the smart shopping basket. Before we'll go to technical details and implementation stuff, we would like to give you a short business introduction to the topic. Basically, some overview, the reason why we have chosen this topic, and why we have decided to build some smart shopping basket. It's not a secret that offline retailers have much more challenges to handle than online shops. And once we will do this distinguishing between offline and online shops, we can see that online shops have much more possibilities to use advanced analytics, to generate more data, and use it further to do some better data science products and offer better products to the customer. And our goal was to find some solution that will also enable these possibilities for offline retailers. And the best example are recommendations and cross-selling. Basically, I think everyone here is aware that once we will log to some online store, and once we will click some products, we have these recommendation sections where we can have some next best offers proposed by the online retailers. And this means that basically once we are logged into the online shop, we are being tracked and our behavior is well known for the retailer, and it can be used to predict some products and give us a better overview what do we really need. But such thing is very hard to achieve for all offline stores, because basically there the shop, the supermarket, knows nothing why we are here, what do we want to buy. They know only these things when we are staying in a queue to the cash desk and when we pay for products we have chosen. So basically we asked ourselves a question: what do we need to change to make offline retailers' life much easier? And we have found one thing, that the biggest limitation is a shopping cart. So basically, we do not want to remove a shopping cart from supermarkets, but we would like to propose to upgrade it to the version 2.0, to the smart shopping cart that is here with us. This is our product, and we think that it enables customers and offline shops better prediction, better behavior, and better analytics in the future.
Professor Andrew Ng, I have a great chance to meet him in San Francisco during the conference in May this year, said that there is a great task to move artificial intelligence from the cloud to the IoT devices to the edge, we can say. What does it mean? Does it mean that for us data scientists, this is real normal? This is quite normal that the place to make AI is the cloud, because we have their GPU, we have their efficient CPUs or something like this. But now the great task is to switch our thinking from the cloud to the AI, IoT. Okay, so let's look at the barriers we have to do it. So I can imagine that you are familiar with deep learning. So you know that deep learning models are very large. We need a lot of computing power to train this model and also to evaluate. normal to evaluate the deep learning model in real time on production, I can say, we need also a GPU. Yeah, CPU is not enough for us. So, ladies and gentlemen, boys and girls, please welcome world first AI accelerator in USB format. What is it? It is Intel Movidius neural computing stick. You can see at the image. And our board, Raspberry Pi, we used. What we used? We used Raspberry Pi, Intel Movidius, and Pi camera to classify, detect, and recognize products. Intel Movidius is small. This is a great advantage, I can say. It allows us to perform a lot of AI tasks at the edge, not in the cloud. Directly, for example, on the Raspberry Pi board. So the key feature is ultra power design. The power from USB port is enough to perform deep learning. It is very friendly for TensorFlow and Coffee. And we don't need to connect with cloud when we want to classify something. And the other advantage is that when we have, for example, 6 USB ports, we can use 6 Intel Movidius as a matrix to provide scalability and efficiency. So, what are the key capabilities for Intel Movidius? We can use it to face recognition, natural language processing, to object detection, to image classification, and also to music generation.
That's a busy one.
Okay, now it's time to show you how YOLO works. YOLO means you look only once, you only look once. What does it mean? That normally when we have recurrent networks, they can also classify images. We can use CNNs, RNNs, or something like this. But they are great, they are working, but the key thing is that first, those networks try to find a lot of squares at the image, and then they try to classify first square, second, third, and so on and so forth. Yeah, it is very time-consuming, and to find maybe 2 products on the image, we need to perform maybe 1,000 classifications. YOLO is the algorithm that we can recognize product only when we look once at the image. Okay, let's take an example. This is a very simple example. This is a real photo we created. We can see 5 products. This is an original image. What we need is to split the image into the grid, into the squares. And then for each square, we need to produce 2 things. The one thing is, for example, 2 anchor boxes. This is, for example, an area where the one cell thinks that there is a product. And also we need to produce the second thing, which is the probability that this square belongs to given product. For example, here, this square belongs to the Oshi drink. Okay, maybe now you can see the 2 anchor boxes at the Oshi drink, and we can also produce the anchor boxes for the area where there is no product. Okay, why not? We did it. Okay, then we also all the time we should maintain the grid. We have a lot of anchor boxes for each cell. We have the many bunch of anchor boxes. And then, at the left-hand side, we have anchor boxes. And at the right-hand side, we have the probabilities that the given small square belong to the given product. And what we need, we have to multiply anchor boxes times the probabilities. And what we have, it is the weighted anchor boxes. And now what the last thing what we need to adjust is to threshold to choose only the higher value of anchor boxes. And those are our products. Okay, how we can train our algorithm. This is, I think, this is known for you that the training is not on Raspberry Pi, but on the server with GPU. So let's look at the code behind me. You can see that the hostname is Atlantis. This is our GPU computer with RTX on board. What we have is we have some files. We have a training file with the training data, test data, label names. Label names, those are, for example, Pepsi, Coca-Cola, or something like this. Images, those are images. Docker file is to use a Docker, and there is also a darknet file with pre-trained white on ImageNet. This is a quick look at the training data. Labels data, for example, this is the name of product. What now? Docker file. Docker file is to produce, to maintain reproducibility and to provide us each for you can repeat our research. And what we need is to check out a darknet repository. Darknet is the original YOLO implementation in the C language. So what we need, those are labels. And what we need is to build a Docker image. Why? Because we provide a custom Docker file. We do a research only with Docker because we want to be independent from our operating system. So we need to build a Docker. We built it a few seconds ago, so we don't need to do it now. What we need there is to run the NVIDIA Docker command. NVIDIA Docker command is very similar to the Docker command, but inside the container we want to use our RTX GPU. So that's why we use NVIDIA Docker. We use disk mapping. This is a volume mapping to provide the data into the container. The data you saw 10 seconds ago. And at the end, we want to run the bash command. Okay, now we are inside the container. You can see the hostname has been changed. This is container. So what we need is to check if we can see the data you saw before. Okay, we have, and you can't see anything. Why? I don't know. I hope that you can see it now. So what we need is to create our architecture. Okay, we can borrow architecture from the authors. And we have to change some things. We have to change a batch file. We have to change subdivisions. This, for example, how many examples we can show for our network. We need to change also how much classes we have, and we need to change also the filters number. Okay, so we are pretty done. So this is also one file we have to create. This is data file, when we can increase or indicate where are the training data, where are the test data, and the label names. Okay, so we're done. And now we are ready to train our algorithm. What does it mean? Does it mean that we can create a command, darknet train, we can pass our data file, then we can pass another file. This is a config, this is architecture, how many layers, how many neurons, or something like this. And then the architecture was printed, and the training has started. So it was at on our GPU computer. So now, how we can deploy this model on the Raspberry and on the Intel Movidius. We are now on the Raspberry Pi computer, as you can see. The trained algorithm has produced the weights file. The last file here is the weights file. And this is the output from our algorithm. The basket config, this is a file you solved before. This is our architecture. Labels names is also known for you. And from the weights file, we have to produce those files. This is very simple. You can use Darknet or Darkflow for it. And now, what is important, we have to use Intel development kit. This is our library you can download, dedicated for Intel Movidius, to compile your trained model to the Intel Movidius architecture. Intel Movidius contain very efficient visual processors, so you have to compile your model, your trained model, into the Intel Movidius architecture visual processing unit. So that's why we called the command. And now the compilation has been started. So what do you need to create such file? You need an Intel Movidius, and you need a library downloaded from the Intel web page to create such file. Okay, and in a few seconds you will see the file which is called graph. This is a ready to load on Intel Movidius file. You can see new green line. This is yellow tooth tiny basket graph, and this graph is ready to load at the Intel Movidius. So how we can evaluate the model on Raspberry Pi? Okay, it's very easy. What we need is to Raspberry Pi, and now, you can see that this is a Raspberry Pi, and now what we need is to load the graph file we generated previously into the USB stick called Intel Movidius. So now we will show you our code in which we capture an image, we communicate with AWS to get recommendations. Michal will tell you something about it, and we also need to load the graph into the Intel Movidius. So this is the file I mentioned. So you can see Intel YOLO tiny object graph. You can see directly dictionary with classes. And what is important, the most important thing is the main method. The first lines are communication with AWS. There we have to initialize Raspberry Pi camera. This is a dedicated camera for Raspberry. And the next step is to run Intel Movidius. This is, for example, to initialize Intel Movidius device. We have to check if the Intel Movidius device is plugged in. And then, from the Intel Movidius device, we need to take an object which corresponds to this device. This is, for example, an object which is an interface for this USB stick. And then, having this object, we can load our graph file we precompiled previously into the device. And this is here exactly. There you can see this is a for loop. Yeah, this is a loop in which we are taking all those images from Raspberry Pi camera, and we are passing each image to the Intel Movidius. Okay, hi Intel Movidius, please produce for me a recommendation. This is please detect all those objects, and all computation related with deep learning are performed inside the USB stick, but not inside the Raspberry Pi processor. And here you can see we are asking each time, for each image we are asking USB stick to detect new objects. So now is the cloud part. So Michal.
So a few slides ago we've talked that it's good to bring computations to the edge from cloud, but in our solution we've used cloud as well. Basically the entire architecture looks like following. On the left side we have the smart shopping baskets, so the entire IoT solution. This is Raspberry Pi with Intel Movidius, the camera and display. And on the right side, we have AWS components. We've decided to use AWS IoT Core and AWS Lambda. So right now, here comes the challenge, how to integrate these all things together. Before we'll talk about it, a few details about AWS components, because maybe not everyone is familiar with that. The IoT Core module is a solution on AWS Cloud that allows us to connect different IoT devices to the cloud. So basically, we are able to send some messages, some data from IoT devices to the cloud and between IoT devices in a network. And also what's really important from our perspective is the fact that it supports bidirectional communication. So we can not only send data from IoT to AWS, but we can also send data from AWS to IoT device. The communication can be done via protocols, for example, MQTT, HTTP, and MQTT with WebSocket. In our case, we've decided to use MQTT. And what's also quite important is the fact that it's serverless. It means that we do not need to maintain hardware. We do not need to think about things like scalability and maintaining the technical part. We just can focus on coding and the core functionality on our application, and the rest is not important for us. Okay, on the other hand, we need some component also on IoT device to establish the communication with AWS. Here we have used the library AWS IoT Device SDK for Python, because the entire development we've prepared in Python language. This is a small teaser, and basically all important methods we used. Connect to establish a connection with a given MQTT topic. Subscribe to be able to receive messages sent on AWS IoT Core, and publish that allows us to send some messages to AWS. So the first step is to establish connection between the Smart Shopping Basket and AWS IoT Core. For that, we have used MQTT, and we have created a topic called products. So every time when the new item is placed to the basket and this item is recognized, there is a message, for example, that this is an apple. This information is sent via this MQTT topic to AWS IoT. The type of a message is a JSON, so the structure is quite simple. This is how it looks like. So we have an information which device sent this message and what was recognized, in this case, product A. And AWS IoT, once the message is published on a queue, is triggering a Lambda function. Lambda is a solution on AWS that allows us to run code without servers. So again, serverless. All advantages that we have described for IoT Core are also valid here. Lambda triggers computation immediately, so we can achieve near real-time solution. And the code is executed only when needed, so it means we do not need to maintain the servers and etc. Every time. We just pay for the time when we really compute something. And it has a great integration with TensorFlow. There are a bunch of articles how to deploy TensorFlow models on AWS Lambda. And we also decided to use it in our solution. So the first model, the YOLO algorithm, is deployed directly on IoT device on the Smart Basket. However, in AWS Lambda, we have used the recommendation engine that is generating recommendation based on the information that was received from the Smart Shopping Basket. And as soon as the AWS Lambda gives us the information about the recommendation, it's sent back to AWS IoT Core. And here on MQTT topic, advice, a different one, which is the Smart Shopping is subscribing, we are sending the recommendation. And once the recommendation is sent, automatically on a small screen that is installed on the Smart Shopping Basket, the image is displayed with the information which product is recommended. This is a JSON file that is sent between IoT Core and AWS on an advice topic, so almost the same structure as previously. Okay, so it's time for short demo.
Yeah, it's time for short demo. I have to refresh my web page. Yeah, I need this web page on my PC, so I will show you another web page, because there are the letters are very small. So what I need is to connect with with my device using the URL address. But before I will do this, I will show you the demo using this presentation. What can you see here is I will show you there. Okay, here you can see how we can recognize the objects. So we can see that we can recognize, for example, the paper, the water, banana, or something like this in each position. Yeah, and also when we, for example, can put inside the paper the recommendation that the next product is, for example, an egg, has been generated. And now I have to connect with my device. Give me 1 second. Okay. Because we have our own Wi-Fi to do it. It's a bit time consuming. So we are quite ready. Okay. Okay, so for example, here you can see, those are a little bit frozen, that in real time we can recognize, for example, that we have two products in our basket. And for example, when I move the product backward, for example, here there is a problem, but because the light is here not so enough, but you can see that, okay, it's good. The left product, this is a left-hand side, your right-hand side product. Okay, this is a camera problem. But you saw that, for example, only using the camera and the yellow algorithm, we can find where the product is only based on the shape and color. This is not important, for example, that there is no logo, for example. Yeah? Okay. We can use, for example, here you see two kinds of sweets. The one, Twix, you can see the logo. But the another sweet, you can see a logo, but we can see the shape, we can see the color of the sweet, and we can make a prediction what product is inside. For example, we have also some other products. If you have time, we can show you something more after our presentation. So now I think it's time to say thank you for coming, and maybe you have some questions we can answer. Thank you.
One very short question is, what is the price of these sticks, or there are any editions or versions?
I can answer this question. Currently there are two versions, the version 1 and the version 2. Since 3 months, we have the version 2, which is more computing power. So the price is $100, I think, at the eBay or Amazon store. You can buy it, but in Poland I didn't see yet any delivers. But using Amazon or maybe official Intel webpage, you can order those things. Mm-hmm.
Okay, so big thanks to our speakers. I think we don't have time for any more questions, so please ask them individually.
Yeah, thank you.
And big applause for them.